Well, welcome everyone for a new talk of the series of IEEE Circuits and Systems Society, chapter Rio Grande do Sul. We have today the pleasure to receive Dr. Corinna Martinella to talk to us about total ionizing dose and displacement damage effects in silicon carbide technologies. Dr. Corinna Martinella received the master's degree in nuclear engineering from the Polytech of Milan in 2016. In 2021, she obtained the PhD degree in applied physics from the University of Jyväskylä, conducting her research at the European Organization for Nuclear Research, CERN, the famous CERN. Her work focused on the basic mechanisms of radiation damage and reliability of commercial silicon carbide power devices for aerospace and high-energy physics applications. Between 2022 and 2025, Dr. Martinella worked in the Department of Information Technology and Electrical Engineering at the Zurich ETH, first as a postdoctoral researcher and lecturer in power semiconductors, and later as senior scientist. Since 2026, she has been an assistant professor at the Institute of Electronics and Systems at the University of Montpellier, France. Her technical interests include the reliability of wide bandgap power devices, testing and modeling of radiation effects, and doping techniques for the next generation of power components. So, Martinella, it's a pleasure to receive you for this talk today, and the floor is with you.
Thank you. Good afternoon, everyone. Thanks for the invitation and for the introduction, and thanks for joining this talk. So today I'm going to discuss with you some of our recent results on work we have done on cumulative effects that we observed in silicon carbide power technologies when exposed to radiation environments. So before starting, I would like to thank the many colleagues and students that have worked with me over the last years in preparing the experiments that I'm going to show you, analyzing the data, and interpret the results. So I'd like to start from the history of silicon carbide, showing you some of the milestones of this interesting material. So silicon carbide was discovered in 1891 by the chemist Edward Godric Acheson. So he was trying to produce and to synthesize some artificial diamonds when he accidentally discovered silicon carbide, and he decided to call it carborundum. It was only in 1905 when the chemist Henri Moissan observed this material in nature by analyzing some fragments of a meteorite that was found in Arizona. It was clear from the very beginning that this material was very interesting and it had potential to be used in electronics and in the semiconductor industry. So in 1955, Lally developed the method for producing a high-quality crystal, which opened up some potential for the semiconductor industry. In 1958, it was the first of many more international conferences where scientists met to discuss the advancements with this material. In that case, was in Boston. And then in 1978, a group of Soviet scientists developed the modified Lally method for the growth of the crystal, which allowed to produce the first crystal which had a commercial potential interest. So after that, the evolution has been broad and fast. We had the first silicon carbide single crystal wafer of 1 inch in 1989, followed by larger dimension wafers in the following years. In 2001, we saw on the market the first silicon carbide Schottky barrier diode, and only in 2010 appeared the first silicon carbide MOSFET. It took some years due to instabilities of the threshold voltage due to the interface. And then in 2018, we saw the insertion of this silicon carbide power technologies into the electric automotive market. So today, this material is used in many different applications, from automotive to photovoltaics and power grids, and it has a lot of potential for also other applications where there is presence of radiation environments, such as in aerospace applications, high energy physics, or the nuclear industries. So this is where we are going to target the talk today, and we will discuss some of the radiation effects that we observe when this material, when these components are exposed to radiation environments. So I'll start by giving you some background about the properties of this material and trying to explain why it is interesting for application in power technologies. And then I will move on to the cumulative effect that we will discuss today, such as the total ionizing dose and the displacement damage. So silicon carbide is a crystal that is composed by 50% atoms of silicon and 50% atoms of carbon. It's a wide bandgap semiconductor, so it belongs to the wide bandgap family of semiconductor together with the gallium nitride, and it has an energy gap which is about 3 times the one of silicon. It has a lot of interesting property, a very high sublimation point, a low thermal expansion coefficients, and it's one of the most famous case of polymorphism, meaning that this material can crystallize in more than 250 different polytypes. Now, these polytypes differ from the stacking of atoms along one axis. They have the same mechanical and thermal properties, but they have very different optical and electrical properties. And so the 4H silicon carbide crystal is actually the one that is target for application in electronics due to the higher mobility of of the electrons along the axis that is used, the phase that is used for electronics. So you already understand that we are dealing with something that is quite different to the traditional silicon electronics, and that the scientists and the industry had to face quite some challenges in order to have a sustainable and reliable commercial process to come to the point where we are these days. This material is particularly interesting for power electronics for the following reasons. So when we look into power devices, we want to maximize a specific figure of merit. We want to have devices that can work at very high breakdown voltage, so sustain a very high electric field, but also we want to reduce the specific on-stage resistance. So we see that this is where silicon devices are placed on this graph. And we can improve this figure of merit following 2 directions. The first is by changing the material. You can see how wide bandgap materials such as silicon carbide and gallium nitride improve this figure of merit. And things get even more interesting with ultra wide bandgap materials such as gallium oxide or diamond. A second way to improve it is to change the architecture of the component and use a superjunction design. So we can see here is the limit of silicon devices. When moving it to superjunction devices, then the slope of this line change. And again, things will get even more interesting when we will be able to produce silicon carbide superjunction devices. In fact, these days, superjunction are only available for silicon components, but they are in different stage of development for silicon carbide. This material has some specific properties which make it interesting for power devices that can improve indeed the figure of merit I just presented. So we say that we have is a wide bandgap material, so we have a large bandgap. And also this material can sustain a 10 times higher electric field with respect to silicon. So overall, this means that in order to sustain the same electric field, now you can manufacture the device with a 10 times thinner epitaxial layer. So overall, you are reducing the thickness of your epitaxial layer. And so in turn, you're also reducing your on-state resistance. And that's why your figure of merit improves. Also, it has a higher thermal conductivity and a higher melting point with respect to silicon. And so this allows to use devices manufactured in silicon carbide at higher temperatures. It has a higher electron saturation velocity with respect to silicon, and so you can switch the component faster. So overall, you can have this technology allowed to have a application at higher voltages, frequencies, and temperatures, and also to reduce the conduction losses. So overall, you're improving the efficiency of your system, meaning that you can manufacture something something that is more compact, and so you're reducing the size and the weight of your systems, and that this becomes particularly interesting, for example, when you need to fly your power converter, for example, on aerospace applications. Furthermore, this material has a higher ionization energy with respect to silicon. And so this makes it interesting also for application in harsh environments. So not only when temperature is high, but also when there is a presence of radiation. As I said, the first device appeared in 2010 on the market, and after that, a few different designs were developed for silicon carbide. We are talking about vertical power components. So we have our gate on top, the channel is formed in the P wall, and the drain is at the bottom. Generally, we have an epitaxial layer, for example, for a device of 1200 volts, which is 10 micrometer of thickness. And then we have a substrate, which is hundreds of micrometer. So we have this planar design. Otherwise, we can have an asymmetric trench device, which is chosen as a design from some manufacturer. And then we have a symmetric trench design. In this case, the channel is vertical. Here we have a single channel, and here we have two channels. Here again, it's a different layout of the component. We can find components packaged in modules in a TO247 package or as bare die. So for the experiment I'm going to show today, we always used bare die. Here is how a TO247 package look like once it's open. And this is an example of a bare die. You have contacts of the source and the gate here, and the drain is at the bottom. However, this is a striped devices, meaning that if you zoom in the active area, what you will see are a series of stripes which are connected in parallel. Now, each of these stripes looks it's a single unit cell, and it looks like this. So you have your gates, and then you have your P wall, as I explained earlier, and the source contacts. So inside the device, you can this design also creates some parasitics there. You have a PN diode, also called body diode here, an NPN parasitic BJT, and a JFET region between the P and P wells. If we take a look, just to give you an idea at where this where silicon carbide power technology are placed on the market. we said that wide bandgap technologies, both for gallium nitride and silicon carbide, works better at higher frequencies with respect to silicon. So they are preferred when you are dealing with high frequency applications, with respect to low frequencies where silicon is still like dominating the scene. Compared to GaN, silicon carbide shares the market, but it covers the segments of the market that goes from 900 volts up to, I think, 3.3 kilovolt commercially available at the moment. Whereas gallium nitride hemmed devices, they are preferred for low to medium voltages, so generally up to 650 volts. So when you really need to work at to have a device that can sustain very high breakdown voltages, then the silicon carbide design is the one that you have to choose with respect to GaN. As we said, this material is also interesting for several applications. For example, for use in aerospace, defense and space, but also for electrification of aircrafts. It has been considered for different missions, space missions. For example, for the Dragonfly mission, which is exploring Titan, one of the moon of Saturn, for the Artemis program, but also for Venus exploration. It has been considered for application at CERN, as power components, but also has detectors, and also for nuclear industry applications, again as power component or as material for a detector, a radiation detector. In all these different applications, depending on which one we are considering, we have different sources of radiation. Generally, when we're dealing with space, the main issue is due to heavy ions, whereas when we are dealing with atmospheric radiation, then we have neutrons that are representing the main issue. We can have a variety of effects that we can observe in this component. So in general, single event effects are the most critical because they can be induced by a single ionizing particle. And then, but we will not cover those now in this talk. We will instead focus more on the cumulative effect, such as the total ionizing dose and displacement damage. Okay, so moving on indeed to the results. So the total ionizing dose is the total energy that is deposited per unit of mass through ionization. So if we are dealing with a charged particle in our radiation environment, that is the energy is deposited through Coulomb interactions. Whereas if we're dealing with photons, then the energy will be deposited through different mechanisms depending on the energy of the photon and on the Z of the material that is absorbing the energy. In general, we can say that for low energy, we are dominated by the photoelectric effect. For medium energy, we are dominated by Compton scattering, and then for high energy, pair production of an electron and positron. Now, the release of energy generates, like the ionization generates electron hole pairs in the material. And for example, 17 electron volt are necessary to create a pair in the silicon dioxide. The total ionizing dose is measured either in gray or in rods. So in this presentation, we will use rods, and we can say that 1 gray is equal to 100 rods. So the total ionizing dose affects the dielectric layers, such as the gate oxide and other insulations layers. And it can cause a parametric shift in the electrical responses of the MOSFETs due to the buildup of the trap charges and the interface traps that are caused by the particle that is ionizing the material. It's a cumulative effect, as we said, which is proportional to the cumulative dose. Instead, when we talk about displacement damage, this originates from the non-ionizing energy loss mechanisms that the particle is having while interacting with the medium. So the particle is transferring energy to the lattice, and it can displace some of the atoms from the crystalline sides. Now, the displaced atoms can generate primary defects, such as vacancies, interstitial, anti-side defects. And these defects, some of them might be electrically active, and they can act as trapping centers. So they can modify the carrier transport properties of the material, such as the mobility, the concentration, and the lifetime of carriers. Again, it's a cumulative effect, and generally when we talk about displacement damage, we refer to the fluence. So number of particles per centimeter square. In this talk, I'm going to present you a series of experiments we have done using X-ray irradiation, so 10 kiloelectron volt X-rays. So we are in the region of the photoelectric effect. And also we irradiated with protons. We use 3 MeV, 3 megaelectron volt protons mostly, but also 1 megaelectron volt protons that I will discuss later. Now, these 3 MeV protons, they have a penetration range in silicon carbide of 57 micrometer, meaning that we are in the substrate. So the majority of displaced atoms are generated, in this case, in the substrate of the component, because the epitaxial layer is about 10 micrometer, as we said. We performed experiments going up to ultra high doses of 100 megarad in the oxide. So these doses are extremely high, and you can only encounter them in specific applications, such as applications that's in high energy physics experiment, for example. However, when we perform the experiment, we always step the dose in different steps, so we can also get data about lower doses and so observe the evolution. And just to say, for space, you are interested into regions of 100 of kilorads. So we tested vertical power MOSFETs from the Cree Wolfspeed manufacturer. They were second or third generation devices. And when we test them, we keep the drain source bias in off state, and we apply a different bias at the gate. Now, we can test them in ground conditions, so we have 0 at the gate, or in on condition when we apply the maximum bias that is possible to apply at the gate, semi-on when we apply an intermediate bias between ground and on, or off condition when we apply the maximum negative bias that is allowed by the manufacturer. So I'll start by showing you the results from the X-ray irradiation. So what we observed was, if we look at this plot, for example, we have here different transfer characteristic, and we can observe that by increasing the dose, we see a shift of the curve towards the left. And so we have here a shift of the threshold voltage towards negative value. And this was due to the trapping of positive charges in stable defect in the oxide. We saw a little bit of recovery after annealing, but not too much. There is a dependency to the bias conditions, particularly to the electric field that is applied at the gate during the exposure. So the charge yield, it's changed with the electric field. And we can see generally when we study this effect, we always look into some specific figure of merit to see how the MOSFET is performing. So we look at the on-state current, the delta of the threshold voltage shift between the different points, the transconductance, and the subthreshold swing. If we take a look, for example, at the delta of the threshold voltage, we have here the dose, so we can see all the step of dose, and we are here the value of the threshold voltage. And so we can see that the worst condition was when the device was in on bias or semi-on. So in this case, the device was either at 20 volt or 50 or 5 volts, and there is not too much difference among them. Then we have the off-state case and then the ground condition. So we also saw a degradation of the transconductance here, indicating the generation of interface drops that cause a degradation of the transconductance of the device and an increase of the subthreshold swing. Similarly, we did the experiments with the protons, and now we not only have total ionizing dose effect, we also have displacement damage. And so you can clearly see that even though we had a shift of the threshold voltage, by the end of the irradiation, we have a drop from the black line to the red one of about 80% of the current of the component. By looking at the logarithmic scale of the transfer characteristic, we can see the shift of the curves, and then we can see a drop of it, so that there is a continuous drop until a saturation level. And so this was the onset of the displacement damage. What was happening this device was that we were having charge compensation. So the carriers were trapped by the active defects that were created by the primary particles. And we can still see that there is some current, and this is due to the fact that below the bonding wires, those cells are shadow, because now our protons have a penetration range of 57 micrometers, so they get stopped in the bond wires, and so those few cells were still conductive, and that's why we can still see some signal there. Once again, there is a proportionality with respect to the bias, gate bias during irradiation. We can see that total ionizing dose, it's, for example, if you look at the delta of the threshold voltage, it's higher when we are in on stage with respect to off state and ground. However, when we the onset of the displacement damage, it's clearly the same independently on the bias that is applied on the gate, because that's a material property. And so we see that for all of them, there is a sudden drop at the same point in the on-state current and in the transconductance. This point for the onset was observed as 6.7 10 to the 12 centimeter square, proton per centimeter square, which corresponded at about 10 megahertz in SiO2. And so what is happening here, you are degrading the series resistance of the device. If we compare X-rays and 3 MeV protons, again, looking at the same figure of merits, we can, at the same parameters, we can see how there was the total ionizing dose induced by the protons was higher. So you can see the red line here, the degradation induced by the proton is higher with respect to the photons that we're using. And then you see this sudden drop in the currents, which you don't observe with the photons, indeed due to the displacement damage and the charge compensation induced in the device. So we say that we are degrading the series resistance of the component, and so we apply the split CV method in order to study the resistance of the device after the irradiation. Now, this method is reported in this paper. But it works as follows. So you have you start from the equivalent circuit of a power MOSFET, and by solving the Kirchhoff system of equation, it's possible to retrieve a relation between the channel resistance, so the resistance of the channel of our device, and the drift resistance, where this drift resistance is due by the sum of the epitaxial layer resistance here, the JFET resistance, and the substrate ones. And so you can retrieve this relationship where the gate drain capacitance and the source gate capacitance are involved, and also the overlapping capacitance between gate and source contact. Now, the gate drain and gate source capacitance can be measured after the irradiation, and so by solving this, it's possible to retrieve the value of the channel and drift resistance and to understand where the degradation has happened. For example, we did that for our devices and for all the different bias condition we had. And for example, we can see here we have the total on-state resistance of our component, which is the sum of all the resistances of the device. We can see this was the pristine level, I think was 80 milliohm. And after irradiation, if we consider, for example, the ground device irradiated at ground level, we had that we had about a factor of 10 increase. No, sorry. We had the value was about almost 2000 milliohm. And then by applying this methodology, we saw that this was all due to an increase in the drift resistance. And so this makes sense because in fact, we are maximizing the creation of defects in the substrate. And so this is, it's creating a resistive layer in the substrate of the component. And so the drift resistance is increasing. From the analysis, we retrieved then the capacitance from our measurements. And by taking a look at those, for example, we have here values of the capacitance. So the input capacitance in black, gate source capacitance in red, gate drain in green for 3 devices irradiated at 100 megarads. So we have the one in on-state, ground, and off-state. For example, if we look at the one in on-state, we have a combination of TID and displacement damage. So we can see that if we look at the input capacitance in black, we have the pristine one in dot line here. We can see that there was a shift towards the left, and this was due to the total ionizing dose. Then we also have a stretch of the bottom part, and this is due to the generation of interface defects from the irradiation. And then the displacement damage show its impact by reducing completely the gate drain capacitance. So there is no more capacitance, it's no more capacitive there, our components. So the gate drain capacitance after irradiation is totally flat, and the gate source capacitance is just equal to the input capacitance. We can see that as well for the device is irradiated in ground condition. Here we don't have TID effect, we only have displacement damage, and we can see how there was the drop of these two curves, like the modification of these two curves. And so then we simulated that. We consider a case with a lower dose. So we considered 15 megarads, which was the onset for the displacement damage, which corresponded to about 10 to the 13 protons per centimeter square. And that's when you can start to see these are measurements, and that's where you can start to see that there is this modification of the capacitance value. So you start to creating defects that trap your carriers. And so we simulated that in TICAD by creating a profile of defects of carbon and silicon vacancies in the device. And the trap level were introduced in the band gap of silicon carbide, and they were determined by either theoretical calculations or by the LTS measurements, which were reported in a previous publication. And so we can see here the results from our simulation, and we managed to reproduce the onset of displacement damage, and so to confirm the measurement. We also compared results from a device of different generation. We said we used Cray-Wall speed devices from second and third generations. So when we look at the degradation of the threshold voltage, so threshold voltage shift, we are plotting results as a function of the dose, and we see exactly the same mechanism between the second and third generation, meaning that there is no difference in the mechanism that is happening there. So we are trapping positive charges in stable defect in the oxide. However, when we look at the subthreshold swing, or at the transconductance, we can see that actually there was a higher increase in the second generation devices, meaning that the third generation devices have a better interface with respect to the previous generation. We did the same, the results before were collected with the X-ray radiation. Then we did the same with the protons, and we basically observed the same results. And also, of course, the onset for displacement damage was happening exactly at the same point for these two technologies. However, you see a different residual current, and this is simply due to the different proportion of shadowing due to the bond wire that we use in our setup. However, we say that silicon carbide has also some interesting properties that allow to use it at high temperatures. And so we did some studies where we irradiated devices and look into TID at high temperatures. So in this case, again, we were using X-rays, and we irradiated at room temperature at 100 degrees C and 175 degrees C. So again, we saw this shift of the threshold voltage towards the left, with a saturation between 110 and 100 megarad. Meaning that we are saturating the possibility to trap holes, to trap more positive charges there. When we are instead irradiated at 100 degrees C, what we start to observe is a rebound of this effect. So between 10 megarad and 100 megarad, we see a rebound of the effect, and so a shift towards the right for the last point here. And similarly, when we are irradiating at 175 C, with also an overall lower degradation. Once again, by looking at the delta of the threshold voltage, we can compare results for devices that were irradiated at in-ground condition, at room temperature, or at 100 degrees C, and in on state. So by looking at the black line, we are seeing the results in ground conditions. So in ground condition, there is not so much going on. The degradation is low, and so there is not a big difference when irradiating at room temperature or at 100 degrees C, and so the two lines overlap. However, when we are in on condition, we are in the worst case in terms of bias. And so we can see that at room temperature, the degradation was quite high, so down to 5 volts for 100 megarad, which again, it's very high dose. But then this damage recovers a bit for 100 C, and lower degradation is observed for 175 degrees C. So when we test, if we test at room temperature, we are actually seeing the worst case scenario. And then we perform some annealing. So this is the results of our degradation of the threshold voltage after the irradiation. So we have here in blue device exposed to room temperature, 100 C in orange, and under 75 in yellow. Here is the annealing for 24 hours at room temperature, so things get a little bit better. And then we have 24 hours at 100 degrees C and 24 hours and 175 C. So if we compare the device that was irradiated at room temperature and annealed at 100 C with the device that was irradiated at 100 C and annealed at 100 C, we see that things are pretty much similar. And the same happens for the annealing at 175 together with the device irradiated at 175. So overall, we concluded that independently of whether the device was exposed at that temperature or annealed at that temperature, the residual degradation was observed to be very similar. And so the temperature there was really the key factor that allowed the recovery of the damage induced by the total ionizing dose. We also looked into different architectures, not only planar, but also trench device. In this case, it was a non-commercial asymmetric trench device. But similar observation were also observed in literature for commercial components. And in our case, we saw that both with X-rays and also 3 MeV protons, the trench device was more sensitive. For example, if we look here at the delta of the threshold voltage, we have in black with the round dots here, the results from planar device in ground condition, and in the triangle there are the results from the trench device in ground condition. And similarly for the on-state current. So we can see how things in this case were worst with the trench architecture. However, once again, the onset for the displacement damage was observed to be similar. One more work on that was done by comparing different proton energies. So we tested with not only with 3 MeV protons, but also with 1 MeV protons. And the idea here was to try to maximize the damage in different regions of the component. So we say that 3 MeV protons have a penetration range in the substrate. So the majority of defects are actually created at the end of the range. It's at this depth. With 1 MeV protons, then the range of penetration is 7 micrometers, so is within the epitaxial layer. Now we have to say that, of course, epitaxial layer and substrate have different doping density as well. We have about 10 to the 18 in the substrate and about 10 to the 15 in the epitaxial layer. So if we look at the TID as a function of those here, we have the delta of the threshold voltage, and we see that things are pretty much similar when we look at things in terms of those. However, if we look at the results in terms of the fluence, we can see, for example, here, this is the on-state current, and the displacement damage for the 1 MeV proton is happening much earlier in terms of fluence with respect to the one of the 3 MeV protons. And this is because now the majority of defects are created in the epitaxial layer, where there is also a lower doping with respect to the substrate. We did the same experiment also irradiating wafers. We had 4H silicon carbide wafers. 3 were irradiated with 1 MeV protons and 3 with 3 MeV protons. The first were irradiated below the onset for displacement damage. The second one was irradiated at the onset, and the third well within the fluence where we are observing displacement damage. So we had different fluences among them. And then we perform deep level transient spectroscopy to identify the defects that were created in the material. So this is a spectra from the LTS signal as a function of temperature, where we can see with respect to the pristine here in gray that there is the formation of different peaks depending on the wafer and on the specific irradiation conditions. Now we analyzed the results. We looked at the effective carrier density in the device after irradiation. Here we report the results for each of them in comparison with the pristine. We can see that with higher fluence, the effective carrier density tend to decrease, of course. And then we also extracted the defect concentration within the device. So all the details are reported in the paper above. But in general, we observed presence of defects electrically active that were related to carbon vacancies and carbon interstitials. Finally, I also wanted to show you this work. In this case, we irradiated devices with heavy ions. So this experiment was performed at ANSTO in Australia using a microbeam. And we selected a matrix of different irradiation. So we had different ions with different energies and therefore different penetration ranges. And we were irradiating wafers. Again, these are the same wafers that are used to manufacture the components. But in that case, we had wafers with different doping. And then we used photoluminescence spectroscopies and Raman spectroscopy to analyze the crystal disorder that was created there. So we used figure of merit such as the relative Raman intensity and the peak of the of a specific peak from the Raman spectrum to assess whether the irradiation has induced some strain and disorder in the material. And so depending on the different irradiation condition, it was possible to identify whether we were observing a compressive or a tensile stress. We report in the paper all the different Raman spectra for all the different ions and fluencies that we used. And it's possible to observe that for some of them, we were also observing the creation of different signatures that are not observed in pristine devices. But for more details, I would refer to the paper. And yes, with this, I will move to the conclusion. So I try to explain you why silicon carbide is a very interesting material, why it's particularly interesting for power application and also for use in radiation environments. However, in order to have a reliable use of silicon carbide power technologies and silicon carbide detectors in radiation environment, it's necessary to understand what are the basic mechanisms of radiation damage. So in this talk, I present you the results from total ionizing dose and displacement damage studies that we have done at ultra high doses with X-rays and protons. We can say that in all these cases, we observe a negative shift of the threshold voltage due to positive trapping of charges in the gate oxide. There is a strong dependence on the gate bias during the irradiation. And also we studied the degradation of the transconductance in order to understand the quality of the interface. We observe a higher sensitivity with the trench power devices with respect to the planar ones. And also we were able to identify the onset for the charge compensation that is induced by displacement damage with different energies, and also to use DLTS and other spectroscopy techniques to analyze the presence of defects and also of strain within the silicon carbide crystal. And so here is just the list of the different works that I present you in this talk, and a few additional interesting references that unfortunately we didn't have time to discuss. And with this, I thank you for your attention and I take your questions.
Okay, so thank you very much for the very insightful and objective presentation, Dr. Martinella. We have two questions right now. The first one is by Lorenzo Piscinin, one of our students. Why higher temperatures cause a rebound of radiation degradation?
Yeah, so of course, so the higher temperatures allow to anneal some of the damage. So you have to think that the last curves here were performed, for example, one was at 10 megarad and the other was 100 megarad. So with respect to the previous points, the device was exposed to radiation for much longer time. And so my assumption is that we were simply allowing more time to the annealing process to happen. And so that's why we are observing these rebounds. Yeah, something else I didn't mention also is we also stress the device, applying a bias and without having irradiation, just to assess whether there was a degradation of the threshold voltage just due to the electric stress, but it's negligible comparable to what we observe with the radiation. But yeah, I would say that there is some dynamic annealing already happening during the irradiation here.
Okay, Thank you. So another question is by Andressa. I was wondering if there are any distinct comparisons between silicon carbide and conventional silicon devices for TID and displacement damage. Does silicon carbide generally outperform silicon in terms of radiation hardness?
I mean, this is a very interesting question. We are actually working exactly on that to get our own data. So, of course, the interface in silicon carbide is much more complicated than in silicon, and it's much younger in terms of, let's say, time to improve it with respect to silicon technologies. So you do see much more defects there. So in that sense, silicon it's better than silicon carbide. However, it also depends a lot on the thickness of your gate oxide. So thicker gate oxide, as sometimes you might find in some power silicon power components, might trap more charges, and so you might have a larger degradation of your threshold voltage, which is, for example, we are currently doing an experiment. That's, for example, what we are observing. So yeah, in general, that so for TID, it depends a bit on the architecture as well. There are a lot of trench, like different architecture for silicon with respect to silicon carbide, so that can also have an impact. And for the displacement damage, you require higher energy for silicon carbide to displace an atom. But then in the end, it's also a matter of the type of defects that you are creating there, whether they are electrically active and trapping carriers. So I can't fully answer to that question, but that's where I would start to look into to try to get a better answer.
Thank you. Well, I'm not from this field. I'm from computer-aided design, electronic design automation. So I have a question which is not technical. It's about your current research group. Let me type it here. Collaborations. So since you started to work on Montpellier this year, can you tell us about your research group there? How many people are you working with you? PhD candidates or any postdoc, or do you have open positions or collaborations you're looking for?
Sure. Yes, I just joined the group earlier this year as an assistant professor, or in France we have this chair the professor junior position. And I joined, I'm in the department of the Institute of Electronic and System at the University of Montpellier, and I joined the department, the group, the RADIAC group. So there are several other professors that are working on radiation effects in other electronic components. So we have several facilities here to perform these studies, X-rays and gamma facilities as well. And it's an historical group working on the topic in Europe. So I'm the person that works on the power devices part. So I'm particularly on wide bandgap. So I will continue my work on silicon carbide, but I will also open up to other materials to try to study effects. These are cumulative effects, but I also work a lot on single event effects. And yes, the idea is to enlarge the group. So we just closed the call for a PhD position, but there will be more opening in the future. And of course, it's always nice to have a collaboration to bring in new ideas and chat with new groups. So if somebody's interested in the topic, feel free to reach out. There is my email in the last page.
Okay, thank you. So Andres, also thank you for the response. If there are no other questions here, you still have time. If anyone wants to type a final question. In this while, I will remember to everyone that we have a long series of recorded talks given the last 5 or more years. So feel free to browse the other talks that we have. And so we don't have any other questions, and I will take this final moment to thank you very much again, Dr. Martinella, for sharing with us your presentation. It was very, very good, very well prepared, and we are glad to have you here. Okay?
Thank you. Thanks for the invitation. It was a pleasure.
So thank you so much.